Welcome to the second introductory section of Mechanics of Materials course. Let me know if you have any questions in the chat box.
It's on live only, sir. Now it's going live. Yes, sir. Sir, now you can open journal. Pen. This one, sir. Just cut. And then journal. Yeah. Now you can write and everything. Okay. Three of them is watching, sir.
Yeah, I know.
You have to type, sir. Yeah, you can type, sir. Watching, sir.
Okay, that's a question on how to draw the shear force diagram and the bending moment diagram. Shear force diagram, what is the relationship between shear force and the applied load? dV by dx is the applied load Q, right? And dm by dx is the shear force. What does this mean? The derivative of the shear force is the slope of the shear force diagram should be equal to the applied load and the derivative of the bending moment should be equal to the shear force. So you use this relationship to draw the shear force diagram and the bending moment diagram easily. Okay, so for example, if I add let's say I have a simply supported beam, the roller and the hinge here, and I have a UDL on top of it. You know that it is a uniformly distributed load, so the slope is a constant. So to draw the shear force diagram, you use a constant shear force, slope of the shear force being a constant as the guideline to draw that thing. So then what happens? It should be a straight line something like this, or a straight line something like this, right? Okay, so now how do you decide which one is the right shear force diagram? So that depends upon what is the sign of Q. Okay, sign of Q here is negative or positive. Okay, so downward acting is positive according to the sign convention here. So the shear force diagram has to be the pink one would be the right shear force diagram, right? Because the upward acting shear force, if I take a section like this is the positive shear force according to our convention in the course. So basically, now what does that mean? The shear force acting at this end will be negative because there is a upward acting force like this WL by 2, and there will be a upward force acting WL by 2 here. This is a positive shear force and this is a negative shear force. So the green line here would be the right slope for this shear force diagram. Similarly, when the shear force is a constant, slope of the shear force is a constant, the bending moment diagram would be a parabolic curve. Okay, because dm by dx is x, if you integrate it, it will be a quadratic function. Okay, so then immediately you have to think whether it is the how the parabola is. There are multiple options. One is it can be a parabola like this, it can be a parabola like this, it can be a parabola like that. Okay, so there are various options here, right? So what you first judge out is what is the slope of the bending moment diagram at the end points, boundary points. Okay, so now if the slope of at the boundary point is finite, then it should be a parabola of this kind or of this kind, and if it is going to 0 at some thing here, it can be a parabola of this kind also. Okay, wherein it to be more precise, this thing goes something like this. Okay, so the slope goes to 0 there, right? So so what you do is then you decide between whether you draw the bending moment diagram above the line or below the line. You look at what is the sign of the bending moment diagram, whether it's sagging or sagging. If it is sagging, what you do is you draw the bending moment on a tension side, and then if the sagging occurs, the bending moment diagram should be at the bottom of the line. Okay, so this will be the right bending moment diagram for this beam. Similarly, if I add more complicated structure, say I have a cantilever with a point load in between P. Okay, so now what happens? It's a point load, the load is not distributed. So here you use the fact that for the shear force diagram, that until there is a load coming on the beam, the shear force is going to be 0. You use the equilibrium equations, and the ends will be 0 up to here. It will be 0 up to here. Okay, and then it is going to be a constant value because you have applied a P there. It's a negative shear force according to the convention. So it's a negative shear force here. So you have it like this. Okay, this is a negative shear force. This is a shear force diagram with P in there. Okay, a shear force diagram is a constant, so bending moment is going to be a linear variation. The linear variation can be, it can have, when the shear force is 0, the slope is also 0. Okay, and there can't be a bending moment in regions where there is no load. Okay, or no reaction forces. So now the question is whether you want it to be like this or like this. Okay, for the bending moment diagram. Okay, so whether you want it to be like this or like this is the question. Okay, now what you do now, again you see whether it is a hogging or a sagging bending moment. Okay, for this case it is a hogging bending moment with a tension on the top side. So this will be the correct bending moment diagram for this structure. Okay, so similarly you have to exploit the fact that look at the slope of the shear force and the bending moment to judge out which is the correct shape for the shear force and bending moment diagram. Okay, that is the key. Okay, you have to remember these relationships in here. Okay. Okay, any other questions? The question as to what is real about moment of inertia. Is something real or complex about moment of inertia? Okay, everything is in real number system. Okay, whatever we do is in real number space. Okay, what is stress analysis is? In mechanics, what we want to do is we want to relate the force, the applied forces, boundary forces to the boundary displacement, to the displacement here. Okay, we saw in the course that we can't relate these two directly because that's geometric dependence and material dependence. So this relationship won't have any predictive capability, and hence we said that we will define a quantity called strain, and we add a strain displacement relationship, right? Strain displacement relationship we add. What was this relationship? This was, if strain was epsilon and displacement was u, you wrote epsilon as 1 half gradient of u plus gradient of u transpose, right? Where it was dou u x by dou x, 1 half dou u x by dou y plus dou uy by dou x, and so on, right? So this is the strain displacement relationship in there. Okay, and then from the force we said that we will define a quantity called stress. Okay, for this we use the equilibrium equations, right? Equilibrium equations was used, which was divergence of sigma plus rho b equal to rho a. Okay, and then we were relating these two through a constitutive relation. Okay, which was in our course it was lambda trace epsilon identity plus 2 mu epsilon, right? Okay, so now solving given a body, okay, applied some force field at some boundary and restraining its displacement at some other points. Okay, restraining the displacement at some other points. We want to find what are the displacement at the boundary. We want to find what is the stresses inside the body, stress field inside the body. That is, we want to find what is u of x, u as a function of x, sigma as a function of x, where x is the different particles that are occupying this body. Okay, position vector of the particles occupying the body in the current configuration, right? Okay, so we want to find what this is. Solving the boundary problem to get displacement and stress field is called as stress analysis. Okay, solving the boundary problem to get the displacement and stresses over the entire body is called as stress analysis. Okay, there's a question asking on whether there will be a horizontal shear stress is developed on a beam. Okay, see, you have to understand something. The shear stress occurs in pairs, right? We saw that in this course also. If we take an element, infinitesimal element of dimensions delta x and delta y in the x and y direction. I am ignoring the third dimension for now. I am drawing all the components of the stresses. There will be a sigma xx stress. This will be sigma xy component of the stress. This will be sigma yx component of the stress. This will be sigma xy. This is the negative direction because it is in the negative normal. Similarly, this is in the negative direction because it's in the negative normal. Sigma xx here, sigma yy there, and sigma yy here also. Right? Okay. Now, for this to be in equilibrium, what should happen? If we take the moment about the point where this two normal forces meet, I take the moment equilibrium about this point. I have not drawn it properly, but let us assume that this is delta x by 2, and this is delta x by 2, and this is delta y by 2, and the top face is delta y by 2. Okay, because that's the resultant normal force will act at that location, assuming it's uniformly distributed along that face. Okay, so now what happens? Now the moment is due to the sigma xy and yx component of the stresses alone, right? So what do I have? I have taking moment about O. I am writing the moment about O point, taking the anticlockwise moment as positive equal to 0. This equation will tell me that sigma xy into delta x by 2 minus sigma xy into minus delta x by 2, okay, or sigma xy to delta x the lever arm. This produces a sigma xy and xy produces a anti-clockwise moment, right? Whereas sigma yx produces a clockwise moment. Okay, minus sigma yx into delta y. This is not the force, this is a stress. So I have to multiply the sigma xy by delta y delta z, and this has to be multiplied by the corresponding area which is delta x delta z, this has to be equal to 0, right? What does this imply? This implies that sigma xy must be equal to sigma yx. Okay, since sigma xy must be equal to sigma yx, okay, these two vertical, in any element there will be a, if there is a vertical shear there will be an complementary horizontal shear. There is an horizontal shear, there will be a complementary vertical shear also. Okay, so that's why even though there is only a vertical force applied, vertical shear coming on this face, if I cut a beam at any section, what happens? If I look at a section like this, there is a distributed shear force acting like this, and hence to complement that there will be a complementary horizontal shear, so also acting in this plane like this horizontally. This is the equilibrium dictated shear stresses. Okay, this is not a reaction force, and hence in the support reaction there won't be a net horizontal force in a first order analysis. If you consider the beam to be, if you do an exact analysis, a straight line deforming into a curved line, there should be a change in length, right? But what we are saying, the neutral axis doesn't have zero strain, right? So there is no change in length at the neutral axis location, which means in the first order analysis there is no secondary stresses due to elongation of the neutral axis. That is free to shorten the beam. That's why we draw always a hinge and a roller here, wherein the roller will move in a bit to accommodate for the shortening that the neutral axis has to see, so that it can remain as a zero strain fiber. Okay, so that is the reason why there is no horizontal force on the hinge or a roller, on a hinge. Okay, hope that helps you. Okay. Okay, so I hope this helps. Thank you. Any other questions? Yeah, what in Morse analysis? What do you want in Morse analysis? Okay, Morse circle in general represents the various combinations of values that are possible for a same stress. Okay, we saw that sigma star, which is a representation of a given stress tensor in star coordinates, can be related to sigma in the unstar coordinates through q transpose, right? Okay. So now basically from here we got some equation for sigma xx star, sigma xy star for in-plane transformation, sigma yy star. Okay, and then we found that sigma xx star minus some quantity, let me say that what it is later, plus sigma xy star whole squared should be equal to r square. Let me say this is c. Okay, c minus r is equal to c of x equal to r square. Okay, where r and c of x were dependent upon c of x was sigma xx plus sigma yy by 2, and r was square root of sigma xx minus sigma yy by 2 whole square plus sigma xy whole square. Right? Okay. So now what we did was we plotted this equation, which is the equation of a circle. Okay. So that is what we are doing here. So we are plotting sigma xx star versus sigma xy star in the y-axis. You get a circle here. Okay, you get a circle here. Okay, with center as c of x and radius as r. How do I know these? Because I know that if I drop it here, this will be sigma xx, this will be sigma xy, and 180 from there, which is 90 degrees in the actual case, this will be sigma yy, and I know that sigma xy, because of the complementary nature of sigma xy and yx that I explained just now, this will also be sigma xy. Okay, this is also going to be sigma xy. Okay, so now from here you know that the center of this line is going to be sigma xx plus sigma yy by 2. So this becomes sigma xx plus sigma yy by 2, and radius is given by cx sigma xx minus c of x whole square plus sigma xy whole square, and the square root will be the radius, which is what we are given as the equation there. Okay, so this is how you draw the Mohs circle. Okay, so you identify the location where sigma xx, all these are positive, I assume positive number, sigma xx, sigma xy, and this will be sigma yy, sigma xy components, and hence we write this in general as sigma of the normal stresses versus this is the shear stress in general. So you write this as the shear stress in general. Okay, and complete the Mohs circle analysis. Okay, so is that useful? And what does each point on this circle represent? The possible values that a particular stress tensor, same stress tensor, can take. Okay, that's what this thing represents. The circle represents possible combination values are the components of the stress tensor. See, when something punctures the other, one thing is supposed to be rigid compared to the other. The one which is rigid is the column here. So that's why the column punctures the slab and not the other way around. And you don't draw horizontal force diagrams, you draw axial force diagrams. It's not only for bars, even if you have a frame structure, you draw the axial force diagrams. Okay, what is the shear force? For example, if I have a simply supported portal, fixed portal frame, the shear force in the beam, if I draw a free body diagram of this, there will be a shear force in the beam subject to UDL, say. There will be a shear force on the beam. Okay. there will be a shear force on the beam, and there will be a moment on the beam. So it will be transmitted to the column as a axial force, and this is anti-clockwise moment, so the moment here is going to be clockwise, and there can be a shear force on the beam, which will be taken as the axial force in the shear force in the column, which will be taken as the axial force in the beam. Okay, so there will be axial forces in a frame structure, just like our arch resists the upright moments only through axial force, development of axial force. A frame also will resist part of the forces through axial force. Since it is not funicular, it is not completely by axial force, there is a bending and axial force coming in there. Okay, so to complete this shear force, to complete this diagram, you will have that's a clockwise, so this is going to be a anti-clockwise moment in here. Okay, and same thing on this side also. Okay. It's a clockwise movement. Okay, so I should have a anti-clockwise movement. Okay. Any other questions? Yeah, questions? There was a question on where do you use spherical coordinates for doing Sandlesses. For example, you want to analyze the blowing of a balloon, say. The balloon expands to become a sphere. So there you use spherical coordinates to analyze the problem. Okay. So for example, if you have a spherical dome and things like that, there you use spherical coordinates to analyze the problem. Okay. So like that, it depends upon the geometry of the body that you are analyzing. That, and if you want to get an analytical solution, and the geometry of the body will determine what coordinate system you use. If you are analyzing pipes or cylindrical bodies, then you use a cylindrical polar coordinate system. Okay, like that depends upon the geometry of the body to analyze, that you are analyzing to decide on what the coordinate system you have to use if you want an analytical solution for the problem. See, all members are 3-dimensional only. You approximate them as 1 dimension or 2 dimensions, and the stresses even in a beam, which is a 1-dimensional member, as a plane state of stress, right? Similarly, a plate, which is a 2-dimensional member, as a plane state of stress, but the stresses are acting on all the 3 directions if you are including the applied loading also. Okay, so basically it is not a dimension of the problem, or it is not whether you are analyzing a beam or a slab or a spherical shell or a cylindrical shell that determines what is state of stress. The state of stress is always 3-dimensional, and you have to know what the different components of stresses mean then. Okay. Okay, there's a question on what is shear center and shear flow. Okay, so now basically we saw that there will be a when I take a simply supported beam. If I take a simply supported beam, subjected to a UDL, we saw that the shear force varies along the length of the member, right? With the maximum being at the support and minimum being at the midpoint of the beam. I haven't drawn this properly. Okay, let me erase it off. Okay, so this will be at the middle of the beam, L by 2. If L is this length is L, that will be L by 2, and this length also will be L by 2, and I will add WL by 2 and WL by 2. Okay, now the question is what happens for different cross sections of the beam. Say I add a I section. Say I had a I section which is built up like this. It's built up like this from wood, say, when you have nailed this flange onto the web. You nail the flange onto the web. Okay. Now, how will you design the connection? How will the shear flow be? Is the question. You know that if it is a rectangular beam with uniform thickness throughout the cross section, what happens from the expression sigma xy is equal to vq by ib, you can construct the variation of the shear force along the depth, which will be a parabolic variation, the maximum occurring at the neutral axis. This will be h by 2, and this will be 3 by 2 times v by bh, right? This maximum shear stress, tau max, will be 3 by 2 times bh. Okay, so we have seen this derivation in the course. Okay. So now what we are seeing is when this is not a rectangular section but the thickness changes along the depth of the cross section, you can't have a continuous flow of shear stresses, something like this in the cross section. It increases and decreases, right? So that kind of a shear flow cannot happen. Okay, so what happens is, because at this corner point the shear stress has to go to 0, here it has to go to 0, here it has to go to 0. So if this is a thin member, you can't have vertical shear stress distribution. So there what happens is, we will have an horizontal shear stress flowing like this. Okay, now how will this resist the vertical shear coming on the cross section, vertical shear will be resisted by the web alone. The flanges will will be subjected to only the horizontal shear stress. Okay, we subject to horizontal shear stress like this. This shear stress flows like a water, right? So if I were to put water on from this end and from this end, it flows like this through the web and goes over to this flange like this, goes out like that, right? So that's why it's called as a shear flow. Okay, these things are dealt with in detail in the subsequent weeks. Okay, so I suggest you look up the subsequent week lectures, and then the last live section, which is the third live section for this course, we will see again if you are not clear about why the horizontal shear stress comes about and so on. Shear center is also defined there, so we will do that later. Okay, the next thing, how to construct ellipse of stress. See, ellipsoid of stress, I presume. Ellipsoid of stress is for a three-dimensional state of stress. What will happen is I can take any two planes and draw more circle. I have three eigenvalues, right? So I can draw three circles like this, wherein this will be the absolute minimum sigma 3, sigma 2, sigma 1, say. If it is where sigma 1 is greater than sigma 2 greater than sigma 3, what this represents is an ellipsoid in a three-dimensional representation. Okay, there are three components. There are six components, and how the six components vary so that it represents the same stress state is given by the ellipsoid of stress. Okay. How do you construct that is beyond the scope of this lecture or this course in particular. Okay, so the cross section is what you represent like this. Okay. Oh yeah, the end shear force is not. The shear force is maximum because in a horizontal, in a simply supported beam subjected to a UDL, we saw that the shear force slope has to be a constant. Okay, so it can be a straight line moving from place anywhere. Okay, but we know from the reaction forces that the reaction to both supports are equal, and hence it has to be in that way. Okay. Okay, failure theories we are looking at in a subsequent week. That has not come up for live session still. Okay, so when that is over, in the next class, next live section, we will look up on failure theories, maximum principal strain theory or Rankine theory and so on. Okay, that's part of this course, but that's covered towards the 11th week or 12th week, somewhere in between there. Okay. No. See, you are confusing between the variation of shear force along the axis of the beam and this is the variation along the depth of the cross section. This is along X, Y and Z. Okay, and this is Y and this is Z. The variation of the shear force along the cross section of the beam. And this is the variation of the shear force along the length of the beam. Okay, this is along the length of the beam, and this is the variation of the shear force along the cross section of the beam. Okay, they are different, they are not the same variations. Okay. Any other questions? A book which is better for mechanics of materials, which has a lot of worked out problems, is the book by Popo. Okay, Mechanics of Materials by Popo is a good book. Gary and Timoshenko is also a good book. Mechanics of Materials by Gary and Timoshenko. Any other questions? Iblis is also good book, but it is a bit old-fashioned dealing of the subject. Any other questions? See, you might be thinking that since you are applying a force like this on the soil, say I have a soil mass, say I am applying a force like this, you might be applying a normal force, but that doesn't mean that all the planes are subjected to only normal forces. For example, in a uniaxial state of stress also, even though you are pulling the bar with the normal stress alone, a 45-degree plane will have both shear stresses and a normal stress, which will be, if this is sigma, this will be sigma by 2, and this will also be sigma by 2. Okay, so it's not that if you apply normal stresses, only normal stresses will be in the body. Okay, there will be planes, other planes that are having shear stresses also. For example, that's why in a Mohr circle, what happens? Only 2 points have only normal stresses, right? That is the maximum and minimum principal stresses point have 0 shear stresses. All the other points have shear stresses in them. Okay, so basically that is the reason why only 2 planes have no shear stresses. All the other planes will have both normal and shear stresses in them. Okay, so basically it's a misconception that if you apply normal force, only normal forces will be there in the soil. Okay, so soil doesn't resist shear, so the failure will be due to shear stresses in the soil, in some plane where there is shear stress in the soil. Any other questions? Any other questions? Usually on a surface, if you are not applying any forces, the shear stresses are 0. That's the reason why I said these points should have 0 shear stresses, right? The reason why these points are 0 shear stresses because these, if you are not applying or in fact even this surface will have a 0 shear force. Okay, shear force or shear stresses, because unless you apply a shear stress, the surface is free of traction, and hence the outside wall will have a zero surface, zero shear stresses. The frictional resistance will give you the shear stress on the outer surface of the wall of the house when it is touched with the soil. Okay, if the soil has some frictional resistance, that frictional resistance will become the force on the wall of the house. Okay. Any other questions? No, RCC beams are designed in rectangular in section. The most effective beam section is the I section, wherein you want to spread the material away from the neutral axis as much as possible to resist the load appropriately, right? So, if you look at steel bridges, they will be made of I sections, okay, and circular sections are also used when there is torsion or some other bending effects coming in there. So, triangle and circular are difficult to construct in practice using reinforced concrete material. Okay, so they are not preferred. Circular section again is not so beneficial for bending resistance, because the more material is towards the center and less of it is towards the outer surface. Okay, so annular cylinder will be a better option there for as far as bending resistance comes about. Okay, so efficiency of the material utilization, ease of construction determines what cross section a beam is designed to have. Okay. Any other questions? Okay, why are you studying statics in SOM and not dynamics? See, the reason is many times the inertial forces are insignificant compared to the applied forces that are coming on the structure. Okay, and they don't vary with time significantly, and hence we study mostly static in strength of materials or mechanism of materials and not dynamical effects. Okay, so but it's not that there's no dynamics considered at all. There's separate course on structural dynamics which handles with the dynamical problems. Okay. Scope of scientists in mechanics of material is to identify the appropriate constellation so that you can be more closer to the material response than what we are doing right now. Okay, that is the main challenge. If you see the equilibrium equations and the strain displacement relationship are well established, whereas only the constellation here is not well established. It differs from material to material. The material response is non-linear. How do you generate those non-linear constellations is a bit unclear till now. Okay, so for these cases we do research on constellations and solution techniques. When the constellation changes, solution techniques also change, and we do research on how to solve boundary problems using more appropriate constellations. Okay. Okay, I thank all of those who are watching this live streaming of the interactive section. Okay, I think it's 6 o'clock now, so we'll wind up the session in a short while if you don't have any questions. Okay, thank you. I'm winding up this session.